got new markers. You shake it. How do you like that? That's pretty great. We're going to talk today about products and quotients when you're taking the derivative. See, taking the derivative of things added together is easy. I'm going to say easy with a plus, like when you're doing derivative of 8x squared plus 17x. You just do each of those separately. The fact that they're added doesn't make much difference. You just do this one, and then you do this one, and that's the answer, all right? There's no special thing you have to do when they're added together. You just do them both separately. When it's a product or a quotient, though, there are special things you got to do. When it's a product, if you're multiplying instead of adding, like right here, you cannot just do the two derivatives and multiply the answers together. I'll show you why. Oh, look at that erase. Unbelievable. Check this out. What if I want to do the derivative of something like x to the 4 times 8x cubed, all right? Now, if I really wanted to do this derivative, I would just multiply it first, right? There's no reason to try and take the derivative when it's written in this strange way. You should just multiply them first. So before I do the derivative, I am first going to multiply these things together. X to the 4 times 8x cubed. The x's combine and you add the exponents. This is 8x to the 7. And so the answer is 56x to the 6, right? This is the derivative. But what if you had decided to just take the derivative of each of these two parts separately? See if they were added. If that was a plus, then you would just do them separately. What about when it's multiplied? Can I just do them separately in that case? The answer is no. Check it out. What happens? If we just were to do them separately, this would be 4x cubed. And this one would have been 24x squared. And if you multiply these together, they would combine and give you, 4 times 24 is 96, right? And then x cubed and x squared will be x to the 5. See, they're not the same. These are different answers. This is right, though. This is the correct answer. This is not the correct answer. So the moral of the story is when you have a product in your derivative, you cannot just take the derivative of each of the two parts. You'll get something, but you won't get the right answer, okay? Instead, you should just multiply them first if you can. But there are many, many situations in which either it's impossible or just inconvenient to multiply the two things first. And you need to use a special rule, and it's called the product rule. Let's talk about the product rule. It's a little formula you'll have to remember, unfortunately. I'll tell you the formula first, and then we'll talk a little bit about where it comes from. This is the product rule. It is about how do you do the product, the derivative of f of x times g of x. It is not just derivative of fx times derivative of g of x. But what is it? I'll tell you what it is. Here's what it is. And this formula you're going to have to memorize. It is f of x times g prime of x plus g of x times f prime of x. All right? You got to remember where those primes go. It's important. This is the first function as is. This is the derivative of the second function. This is the second function as is, and this is the derivative of the first function. Usually when I say this sort of out loud, if I'm telling a bunch of people what the product rule is, I say it's the first thing times the derivative of the second thing. These are the two things. First thing times the derivative of the second thing plus the second thing times the derivative of the first thing. Let's just do an example. Like I said, this is super important. You should memorize that. Hopefully you'll do enough examples that you will just sort of naturally remember it after a while. Let's do a specific example. How about the derivative of, try this, x plus 4 times 5x cubed minus 7x plus 6. All right? This is a multiplication on the inside. Now, it is possible in this case to multiply these guys together first and then take the derivative at the end. That's kind of a pain, though, because of this sort of a FOIL thing. You have to do the FOIL with three things here. you get 6 parts and then you take the derivative of each one, is possible, but it's a bit of a pain. It's a little easier to do it using the product rule. So when I do the product rule, this is the first thing. This is what is playing the role of f up there, and then this is playing the role of g. Let's just do it. You plug into the formula. It says f of x, that's the first thing exactly as is, x plus 4, times g prime of x, that is the derivative of the second thing. The derivative here is 15x squared minus 7, right? The 6 goes away because it's a constant. I hope you put those parentheses in there, haters, because it's important. If you leave those parentheses out, then you will miss out on some distributing, and it means something different. All right, I did f of x times g prime of x. That's half of it, plus, this is plus in the formula. And now I go g of x, f prime of x. G of x is the second part, which I write exactly as is. 5x cubed minus 7x plus 6. Finally, times f prime of x is the derivative of the first part. The derivative of x plus 4 is 1. The derivative of x is 1. The derivative of 4 is 0. So this is times 1. Doesn't really matter. All right, that's the answer. This is the derivative of the product. You can try and simplify that if you want to, although I don't think there's any good reason to. I took the derivative. If it's your job to take the derivative, take the derivative. That's the answer. I wouldn't simplify that unless somebody specifically told you to. All right, this is how you do the product rule. There's not a whole lot to it. It can be a little bit confusing. You got to remember the formula, though. We should talk a little bit about where this formula comes from. If you look up in your book, you'll find sort of an algebraic derivation of the product rule, which is, in my opinion, not very enlightening. It's a bunch of equations, and you work it out, and you get that formula, although it doesn't give you much of an idea, you know, sort of deep down in your heart of why the formula should be true. I'm going to try and give you a geometric sort of a proof, not really a proof, geometric demonstration maybe of why you should believe that the product rule is true. Derivative, of course, is the rate of change, how fast the f of x times g of x changes. This step here, you could think of this as meaning how does f of x times g of x, look at that, whack f. F of x times g of x how does f of x times g of x change when x changes, right? That's really what the derivative is all about. How does the function change if you change the x a little bit? In this case, the thing I'm taking the derivative of is this product, f of x times g of x. And here's how we're going to imagine this. How do you look at, geometrically speaking, multiplication is usually, in a geometric sense, is about area, right? So I'm going to think of a box here where the base width of this is f of x and the height here is g of x, all right? And the question is, how does, and the area, of course, the area here is f of x times g of x, all right? And the question is, how does this area change if I were to change the x a little bit? Let me draw another picture here. I'm trying to look at how will this area change if I change the x a little bit. Now, if I change x a little bit, this f of x will change to become, let's say, you know, usually we write it like this. Instead of f of x, which is that, this is f of x plus delta x, right? I change the x by a little bit. That changes this side by a little bit. In my picture, I made it getting bigger. It could have gotten smaller, but it doesn't really matter. The geometry works out the same either way. So let's imagine that when you change the x a little bit, this side gets a little bit longer. A similar thing will happen with the g. Let's say that represents when you change g of x to g of x plus delta x. All right. The question that I was trying to ask was, how does the area change when that happens? Well, the area used to be this green box. What's the area gonna be? Get my colors going. Gotta shake it. All right, I shook it. What's the new area? It's this, right? You with me here? Okay. How did the area change? Well, you just look at the picture, okay? The area changed by how much? Well, this much. This little sort of snaky thing on the edge. That's how the area changed. You can break that into 3 pieces, though. I'm going to break it up like this. So there's that piece, this little guy, and then this one. All right? The area changed by this plus this plus this, right? Those are the 3 pieces which make up the change in the area. And you can look at this picture and say what each of those 3 areas are. If I call this little distance here, let's call this delta f. All right? That's how much the f changed from going from f of x to f of x plus delta x. It changed a little bit. I call that delta f. And this here, I'll call delta g. All right? This is kind of like the derivative of f, because this is how much the function changed when you change the x a little bit. That is to say, the rate of change of the function f. And this is like the derivative of g. How much the g changed when you changed the x a little bit. Anyway, what are the areas of these 3 different shapes? Well, let's just do this one first. This one is a rectangle. Its height is delta g. Its width is f of x. So this one here is, can I just write these 3 things in order? It is, I said the width is f of x. The height is delta g. So it is f of x times delta g. All right, that's this one. This one here is delta f on the bottom and delta g over there. Delta f times delta g, that's the area of that little piece. And then this one over here is, the base down here is delta f, the height is g of x. So the last one, g of x times delta f. All right. Now, I'm drawing a picture here. Really, you have to think about this picture in the limit as these little pieces are going to 0. That means this is very, very small to be to the point where this becomes negligible when you take the appropriate limits. And then what are these? Well, what's left over? Remember I said this delta f is really like the derivative of f, and this delta g is like the derivative of g. And so what it says is the change in area is f of x times the derivative of g, which is g prime of x, plus g of x times the derivative of f. And ain't that the product rule? Yes, it is. This is the product rule. That's the formula I told you a few minutes ago. This is what I said. This is a geometric explanation of why the product real, it's so real. Why the product rule is true. All right? It's because of all this. Okay? Anyway, that's the product rule. We did an example. It's pretty straightforward to do examples of the product rule. Next, I want to talk about quotients. The product rule is when you multiply things, you got to use the product rule. What about when you are dividing things? Look at this marker erases. I don't know if you feel how awesome these markers are. I hope that you do. That YouTube money is going to start rolling in when they see my new markers. What about quotients? What I'm talking about today is the product rule and the quotient rule. So, a little spoiler alert. There is a similar thing for quotients. Quotients are about this. What about when I am taking the derivative of one function divided by another function, all right? If they're multiplied, you use the product rule. If they're divided like this, you use the quotient rule. And I'm just going to tell you what the quotient rule is. This one is slightly more complicated to derive the formula, but it's a similar thing. I don't think we need to go through it. If you want to see it all worked out, you can check out the textbook. I'm just going to tell you what the formula is, and we'll do some examples. So it is g of x times f prime of x minus f of x times g prime of x divided by g of x, the whole thing squared on the bottom there. All right, this is the quotient rule. The formula is a little more complicated. It's a little harder to remember. Actually, I hope you don't mind me showing a little vulnerability here. The formula here, I have a hard time remembering the formula for the quotient rule, and so I have this little stupid sort of a sing-songy thing that I do in my head. Here's how I remember the quotient rule. If you look at this as the derivative of two functions and you call them high and ho, high on the top, ho on the bottom, the answer is ho. Here's how I remember this. Ho d high minus high d ho over ho ho. That's the g of x squared. Is ho, ho ho. Ho squared, if you will, but ho ho is more fun. Ho, even when I was just writing this just a moment ago, in my head, in the privacy of my own heart, I was saying this in my head to remember what the formula is. You don't have to remember it that way. If you feel like this is too stupid for you, that's perfectly fine. I provide this just in case it's useful. Anyway, this is the quotient rule. This is what you have to use when you are taking the derivative of a fraction. Let's try some examples, and that'll about do it. I got two examples. One is, fairly easy. The next one is a little harder. What? Yeah, there we go. All right, here's the easy one. Derivative of, let's say, x squared plus 3 over 2x minus x to the 7. All right? Easy because really all you got to do is plug into the formula for the quotient rule. I hope you got it written down. You're going to have to memorize this eventually. What is the formula? It's ho d high minus high d ho over ho ho. So the bottom is g of x. The top is f of x. Remember, the format to fit this into is f divided by g. Really, all you got to do is plug into the formula for the quotient rule. What does it say? Look at what it says. G of x times f prime of x minus f of x times g prime of x over g of x squared. So it begins with g of x, 2x minus x to the 7, times f prime of x, that's the derivative of the top, which is 2x, right? Minus f of x, which is x squared plus 3, times the derivative of the bottom. The derivative of the bottom is 2 minus 7x to the 6. That's the top of the quotient rule. All of this divided by g of x squared. That would be 2x minus x to the 7 squared. All right? I hope you got all of those parentheses in there. All of these parentheses are necessary. If you left any of them out, then you are writing something which is not quite the correct answer. All right? The parentheses indicate that if you wanted to simplify this, which I do not suggest, but if you wanted to simplify, you would have to do a bunch of distributing. If you didn't write the parentheses, you'd be talking about something else. So I hope you wrote it this way, you parentheses haters out there. All right? This is what I said was the easy example. I said I was going to do two examples. This is the easy one because all you really had to do is just plug into the formula and that was it. Let's try one that requires a little bit of finesse. This is the derivative of x plus 1 times 3x squared minus 3 divided by 3x minus 1. All right. What's harder about this one? What's harder is it's still a quotient, right? I got this big old bar here. It's a fraction, but inside the numerator of the quotient is a product, all right? This is a little confusing, but what it's going to require is the quotient rule because it is, overall, it is just a fraction. As part of that quotient rule, I'm going to have to use the product rule, all right? Maybe it sounds more confusing than it really is. Let's just work this out. So I use the quotient rule because it is a giant fraction. So I begin the quotient rule by doing the bottom, 3x minus 1, times the derivative of the top. And right here, the derivative of the top, I have to use the product rule when I do the derivative of the top. See, it's a little confusing. I am about to take the derivative on the top, and here I have to use the product rule. Remember the product rule? It is the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. So that's what I'm going to put inside these brackets here. The first thing, x plus 1, times derivative of the second thing is 6x, plus the second thing, 3x squared minus 3, times derivative of the first thing is 1 times 1. All right? All of this inside the brackets was the derivative of the top, okay? Now we continue with the quotient rule. all of that was just part of the quotient rule. The bottom times the derivative of the top. Now I go minus the top times the derivative of the bottom. I'm kind of out of room here. Would you mind if I kind of stretch this out here? I hope your paper is bigger than mine. Minus the top is x plus 1 times 3x squared minus 3 times the derivative of the bottom, which is 3. Sorry, my squeaks. Maybe these markers aren't perfect after all. All right. Almost done. This is not quite done. This is only the numerator of my fraction for the quotient rule. All right. So all of this is the numerator over the bottom squared, which is that. There we go. All right. That's how we do the quotient rule. This is a little bit trickier with that business about the product inside of the quotient, but I hope you can keep it straight. That's about as hard as they get, though. I think that's all. The quotient rule. What is it? Look at the formula in your really all you got to do is plug into the formula for the cronut